Does anyone want to hear any more of the Israel Halpern story? Okay, why don't I just from the a bit or the interview? The interview is a little more alive, right? Okay. All right, but they're both pretty lively, I would say. So we were just looking at the discussion about von Neumann and Wigner. By the way, you might want to look up. I mean, von Neumann and Wigner are both important characters, both important personages of the 20th century. And the American Mathematical Society has a movie about von Neumann, which you can probably bring up on the web. And part of it is an interview with Wigner. And I think it might be in this interview that he tells the story of a joke he played on von Neumann once. And you can decide yourself how funny it is. Okay. It was a brain teaser. You have two, and it's probably parental guidance. Okay. You have two locomotives on the same track, running towards each other, at each one going at 50 miles an hour. And there's a bee flying back and forth between them, say, and they're 100 miles apart. Okay, and there's a bee to begin with. The two locomotives are 100 miles apart. I work in miles. I think in miles, and there's a bee flying back and forth between them, between the two locomotives. So the question is, how far does the bee fly? Okay. This story isn't over. The story continues, but von Neumann answered immediately. And Wigner said, "Oh, you saw the trick." Okay, well, how many people see the trick? Yeah, right. Yeah, do you want to explain it, Vince?
I guess you also need the speed of the bee, but because they're exactly 100 miles apart and they're both 50 miles, it flies for 1 hour regardless of how many times it goes back.
Okay, so the bee flies how far?
I guess depends on the speed of the bee, I guess.
No. Okay, but I put that in. That was 100 miles an hour.
Right. So exactly 100 miles.
Yeah, a bit. Yeah, right. Exactly.
Yeah.
Okay. So this is something that it's believable. It's believable that someone would see it quickly and give the answer quickly, right? Okay. But von Neumann's reply to that was, "What trick?" Simple arithmetical series. I guess arithmetic or geometric. I don't even know. Maybe reverse geometric. You know, I should be able to see something like that, right? But if someone wants to comment later today, whether it's exponential, whether it's linear or geometric, my guess is it has to be linear because it doesn't seem to be too much exponential. Okay. And our last discussion was how you define the inner product. So Halpern asked Robertson, how do you define the inner product if you have complex numbers? And we prove that now. And we've agreed that complex numbers are important. For instance, even important not because they're more complex, because they make things simpler. The group of invertible elements is connected, for instance. So the K1 group is 0. You have to check matrices too, that the group of invertible matrices is connected to over complex. Everyone clear how to do that? You've got to use polar decomposition. Every invertible is a product of a unitary and an invertible positive operator. And both of these are diagonalized, and the diagonal ones are easy to connect to the identity. If you didn't know polar decomposition, it would be might be a problem. You can also use polar decomposition in the formula for integration, of multivariable integration. That if you how does the linear transformation affect the integral? Well, what's important is the determinant. Of course, you have to value the determinant. But how do you see that? Well, one way is to show that there's a multilinear relation coming in. The integral dependent, but it's much easier just to realize that it's certainly that it's just going to be iterated. You change variables twice, then you multiply by two numbers. So what's the determinant? I guess is the only multiplicative function on matrices. So, but to prove that works, you've got to be able to show the determinant determines how you that's a good name for the determinant. Determines it. Yeah, okay, but it does determine, to prove that it determines the how the change of variables factor. You want to show the matrix is a product of a unitary and a positive. This is true. This is true for matrices with real entries too. Polar decomposition holds for matrices with real entries. Okay, Tucker, did you participate in the activities that went on, such as those in the common room? Oh yes, the common room was a wonderful place. As I said, we were all poor. All the students were poor, but I didn't see any trace of competition or friction. It seemed to me we were all monks in a monastery, all working with the purest motives to discover mathematics and to share it with others. The common room was a very lively place. Those were the days when refugees were coming out of Europe. And those in the early 30s, 33. And those in mathematics seemed to head first for Princeton because the Institute, the university's math department were both there. Tremendous concentration of talent. There was hardly a day that we were in the common room we wouldn't see a new face and ask who that was. And the answer would be some mathematician we'd heard of who was a great researcher. Was Stan Ulam around at that time? He wasn't around when I came. He arrived later. In fact, when he arrived, I was deputized to show him around. I remember taking him, among other places, to the gym where you could go swimming. I enjoyed swimming enormously, so with great satisfaction, I showed Ulam the possibilities of going swimming. He turned his nose up at that. He wasn't interested. Well, Ulam wrote an interesting autobiography. And one of the, I think we've discussed the Monte Carlo method. This was a method for doing computations with limited resources, which Ulam first later developed. I used in the atomic bomb project by Ulam. Tucker, I think Bev Blaine had me meet Ulam when he arrived by boat. Might you have come along with me on that trip? No, the first time I saw Ulam was when I was called by Lefschetz and told to take Ulam around and show him the university. Even just reading something like this after 100 years, it's really I find it quite fascinating to just see the names appearing in all of you. But another one being Lefschetz. Right? Probably everyone has heard of the Lefschetz fixed point theorem. Oh, okay. Now, what did we talk about last time? One of the things we talked about last time, so what periodicity works for any complex Banach algebra, right? By the way, I'm taking it for granted that now that in the early days there were people sitting very far back, but I'm taking it for granted now that everyone can hear me. Yes, and I think the broadcast. Broadcast recording. Okay, so what's the simplest non-zero Banach algebra? I mean, I guess zero is a Banach algebra, but it's a little about periodicity. Everything would be, most things would be zero. Okay, but we're looking at complex Banach algebras. What's the archiprava? What's the next most simple Banach algebra?
Complex plane.
Yeah, right. And when you say plane, of course, you can multiply complex numbers, and you can see how to do it in a plane, right? You multiply by I, but what geometric operation is multiplying by this square root of minus one?
Counterclockwise multiplication by pi
By which?
by pi by 2.
Yeah, okay. Pi over 2 or pi over 4?
Pi over 2.
Pi over 2, okay, good. Thank you. Pi is 180 degrees. I think in degrees. I used to even carry a protractor around with when I was in high school. There are two square roots of minus one, right? Would it be the same for both of them? So the difference is that one of them is minus the other, right? One of them is the negative of the other. Oh. And what does the multiplying by minus one do? Well, it just sort of flips through the origin. Okay. And so if you rotate one way, then flip, it's the same as rotating the other way. Okay, good. Well, okay, so the complex numbers form a field. And any field has a K0 group. I guess we've agreed that the K0 group is always the same for a field. The K1 group varies a lot from for different fields. The real numbers, it's not zero. For the complex numbers, it's zero. And what about if we start taking suspensions? If we take the suspension of the algebra complex number, that's continuous functions on the, well, you always have to decide which is more convenient, but talk about functions on a line or functions on the circle. Zero with a point, zero is a standard point. Well, I guess suspension would be on the circle, it would be it's easier to understand running a unit to continuous functions on the circle. The binding should be point. And if you just look at the suspended algebras, continuous functions, complex value functions in a circle, which are zero at the special point. one on the complex. If you join a unit, then you get one function, which is your functions that are arbitrary values at the special point too. So it's arbitrary values everywhere. It's all continuous compact values on the circle. And that, if you want to look at invertible elements, very often that's where you have to look. And I guess we've agreed that since you look at continuous functions from the circle and complex numbers, then this one can be thought of as the circle contained in complex numbers. Then the function S1, any function S1 going to S1 is a complex value function on the circle. And if it's the identity function Z of Z equals Z, I guess look at the homotopy classes of functions, S1 then you can have any power of Z. And that's how the integers come in. That's why the integers are the one of want to know what K1 of the suspension is, you find the one above, and that's what, after all, that's what this, that's what periodicity says. That K1 of the suspension is the same as K0 of the algebra, which is Z. We agreed to K0 of the complex number. Okay, so we're getting enough K1 elements to get Z. Okay, we want K1 of S and C isomorphic to K0 and C. Well, I guess if we take the homotopy theory maps from the circle to itself, if we take that for granted, and that there's a trick for considering those, right? You look at maps from the circle to the circle. You can think of them as maps from the real line to the circle, and if it's maps, so and they be maps such that the say the we were talking about maps where you take the special point to the special point, and the maps R into the circle would take 0 into the special point, and then they could take there'd be always some integral point before it's taken into the special point. So you have and if you stretch this flat, then the arbitrary map would be, you can see the arbitrary map is homotopy to one which is just linear. That's where the Z to the end comes in. The end. But, so let's say that that's elementary. We can take that for granted. But why is that? Why does that not prove plot periodicity? Okay, for the complex numbers, we want to get one S. Obviously, this is where you're going to get the Z if it's true. Okay. But for instance, how do we know that we just look at that Z and the Z identity map? How do we know that when we go to matrices and put that in the upper left-hand corner? How do we know that closed path of the variables is not homotopy? Even these variables, what's not homotopic inside the invertible matrix value is paths, closed paths. Homotopic to the one constant the identity matrix. And now it turns out that this is not as bad as you might. There's an easy proof of this. Okay, it doesn't apply for general C-star algebra. It applies in particular for the complex one. Because the proof for the complex numbers that this is never trivial, or even to the end. That's the end for n not equal to 0. Never going to be, no matter how large matrices you go to, it's not going to be homotopy to the trivial closed path, just a simple constant, single point. So, does anyone want to suggest what an simple argument might be? And let me say this much by way of a hint. We've already discussed the determinant today, and the determinant is obviously quite important, right? Well, there's an argument involving the determinant. If you take Z001, then it's not homotopic. That closed path on the circle Z goes to Z001. That path is not homotopic to a constant path. What's the trick? You might, okay, if some of you are particularly fast and ambitious, you might say, what trick? Let's talk about
Determinant, taking the determinant of that path gives the.
Okay, yes, that's you saw the trick. Okay, but if you don't see the trick, that means you've got to go through the whole proof of injectivity for Bach periodicity. This is a case of injectivity, which we haven't even discussed. We've discussed surjectivity for the general Bach periodicity map, going from K0 of the algebra to K1 of the suspension. And we've discussed very roughly how to prove that that map is surjective. But we haven't discussed the proof that it's injective. Well, it turns out that that's no worse. If that's a complement, it's no worse than the proof of surjectivity, because you can deduce it from surjectivity applied to the paths parametrized by the interval. So in the general case, it's true. By the general proof, it's true that this map is like taking that to the end of this path to the end into the K1 class. That's injective, which is exactly saying that this path is not on the top, either in M2 or in M100. Any size of matrix, that path is not a constant through invertibles, paths of invertibles. We want to do fairly elaborate argument. The argument in the book is about moderately elaborate. There are a number of other proofs, by the way. If someone is thinking of an essay, either essay number 1 or 2 or 3, then it's worthwhile looking up another, might be worth interesting to look up another proof of Bach periodicity. For instance, there's a proof by Nelson Nest. The title has the word Heisenberg. Okay? That should be enough. in the case of, well, we're not finished yet. We haven't proved surjectivity, right? So what Akrapava is pointing out is that if you get injectivity, that this path is homotopically trivial, its determinant, which is also a closed path of complex numbers, non-zero complex numbers, that would be homotopically trivial through closed paths of invertible non-zero complex numbers. But we know that Z to the nth is not. That follows from this what we're calling elementary picture, okay? Elementary plane geometry. And of course, at some point, someone might want to see proof of what goes on here, actual calculation of the homotopy classes maps. Sorry, from continuous maps from S1 to S1 take the special point to special points. So, okay, so is everyone happy with the determinant proof then that this injectivity, the map from K0, K1 is yes,
What breaks down for other rings if we didn't have, if you were to?
well, that's a very good question, but we're the determinant of a matrix it's a familiar object when the matrix has entries in the field, right? But and also, in fact, if the matrix has entries in a commutative algebra, then the same properties hold. But if it's entries are in a non-commutative algebra, then you're out of luck. Okay, so that you have to go a lot of work then, and we have to do that work anyway. We want to prove that an arbitrary path is homotopic to one of these. Okay, that's the other side of the coin. That the math is not in the injective. The first thing you prove is surjective. And in fact, actually injectivity. Let's try and prove injectivity just by group theory because. Well, the trouble is this group might, for all we know, this group might be zero. Then it's not injective. Okay. If we know, as soon as we know that this is not zero, one of these is not zero, then we have a map from Z into something which is well, it might be zero. It might be zero on some. If it's not zero on any of them. It's not zero on any of them. Then it's going to be injective because we know what the domain is. It's Z. To prove that prove the map is injective from Z into something. You only have to prove. You know what the elements of the domain are. You just have to prove that each integer maps into something non-zero. Okay, the permanent argument taken care of. Surjectivity. Injectivity is fine. Well, as far as I know, you have to do the Reship's question now takes root. There's nothing that really seems to distinguish the complex numbers from the general algebra. Proves surjectivity. You might think, so you have to show you have a closed path of invertible matrices or unitary matrices. Okay? and you have to show it's homotopic to this, to just z 0, 0, 1, or z to the n 0, 0, 1. Or some larger matrix ones down the diagonal. Or you could have different numbers, you could z in different places down the diagonal, single just z to the 1 in n places. That would be the same, that would be homotopy. You have z 0, 0, z, and you can homotop, you can rotate that second z up the first one, turn that into a z squared, and then you got one there. So you just have an arbitrary path. And some non-trivial work. Yes, stringent, non-trivial work. Now you could use the fact that the algebra of matrices is a phenomenon. And if you look at it, the type 1 factor, it's a finite type 1 factor. Factor means center of the scale. Common expression. Phenomenon theory. And if you want to have something which behaves in a similar way, you can look at the type 2 factor, finite type 2 factor, which also has a trace, just like the finite type 1 factor, which is matrix. Now, the type 2 factor has a trace, but doesn't have a determinant. But here's something that might also make right. Smith. A long time ago, before periodicity had been generalized from the commutative case to an arbitrary Banach algebra. Okay. And they didn't even recognize it as what's called Bach periodicity. They just proved Bach periodicity in the case of a finite factor. Bach periodicity for a finite factor. That would include either a finite matrix algebra, including the complex number. That would be proving the surjective defense. They would be aware of the determinant matrices. They didn't even concentrate on matrices, they concentrated on the type 2 1 case, the finite type 2 case. The algebra has almost all the same properties as a matrix algebra, as a complex. No, it's not commutative. But there's a spectral theorem. In an arbitrary C2 algebra, you won't have a spectral theorem. Well, you do, but not in terms of projection. You don't have projection. But, Rocky and Smith. By the way, one of the Smiths, this smart aleck who suggested improving on Dijksmeer's terminology of generalized integers. That in itself doesn't prove he was a smart aleck. The fact that he went to Germany without his passport when he was visiting Denmark for some time, and then came back. And this is before the European Union. And then just using his Danish insurance card. And the other Smith is his wife. this is very I haven't practiced this Smith. Fuji Hiro Araki died recently, was a remarkable mathematician. Well known, very popular. Well, okay, one could try to rediscover the elementary. You see, the proof of Araki, Smith, and Smith was relatively elementary. It could be worth experimenting yourself to see if you can somehow jiggle the path, or give the closed paths of unitaries. In some non-commutative matrix now, and you want to somehow jiggle it, perturb it. And you know you're going to have to go to a larger matrix. In the 2-1 factor, you don't have to go to a larger matrix. The reason you know you're going to have to go to a larger matrix now is because you get for Z times some projection, 0, 0, 1. Is it already in 1-by-1 matrix? You can't do that. You can get Z to the nth, but you can't get if you start with Z to the nth, you can't get Z. No room. So you have to go to a larger matrix now where it's true. But it's not a big deal whether you have Z all in one place. In any case, to do that, you need a larger matrix out to get the Z's in different places. Well, so why is it possible in the 2-1 factor? And it's finite. The trace of the unit is 1. So it's not as if it's large, but it allows you to zoom into arbitrarily small things. Okay, you can have projections with arbitrarily small trace, which you cannot have in a matrix algebra. Trace of a projection, even if you normalize the trace to be 1 on the unit, which n-by-n matrices, no non-zero projection can have a trace any smaller than 1 over n. Right? But in 2-1 factor, you have trace small. And this is why given as vertical unitary be formed inside the algebra without going to matrices. Get a well, to get the path, which is well, you're going to need Z to the nth. You're going to need Z to the nth. Z to the nth times B. Well, okay, but then in the matrix algebra too, in the matrix algebra too, if you're going to allow a power of Z, then you can do it. I guess you can do it. You just so in a sense, Rafi Smith and Smith proved the stronger statement. I mean, you can easily write down I guess you can write down the final thing. If you have an arbitrary K0 element, you can write it down in form that both greatest demand gives you, but just with unitary elements in the algebra, paths of unitaries in the algebra. But you're going to have to use power things. finding it. But you have to check that the answer can be written down inside the algebra. You have to check that the deformation can take place inside the algebra too. Okay? You have a given path inside the algebra, path of the variables, and the final path is going to be something like this. Don't know ahead of time what it's going to be, but okay, that's the idea. And then you know that the periodicity says they're in the general proof says general statement says they're homotopic in some matrix algebra. Raki, Smith, and Smith for sure it's homotopic in the matrix algebra itself. It's really a visual contribution. Aside from being the first discovery, you know, of the generalization of periodicity to the non-commutative case. It wasn't recognized as that for a long time. Yeah. Oh, I guess we were.